Hello everyone. Today we're going to be learning about the fundamental trigonometric identities. They should mostly be familiar to you. This should be a more of a review than a first encounter. As you know, an identity is basically an equation, but it's just one that happens to always be true. And these fundamental identities are going to be extremely important because the more complex ones, which we will look at in the next section and the next video, are going to rely on us being extremely comfortable with these fundamental identities. So we'll start off with what we call the reciprocal trigonometric identities. And again, this should be familiar. If you recall, cosecant of theta, for example, equals 1 over sine of theta. We also know that the secant of theta equals 1 over cosine of theta, and cotangent of theta equals 1 over tangent of theta. As simple as these are, you'll want to be very comfortable with their various incarnations. For example, if we imagine a 1 under each of these expressions on the left side, then we can go ahead and cross multiply, and we end up with sine theta cosecant theta equals 1. And of course, we could have written cosecant theta times sine theta. The order of multiplication doesn't matter because of commutativity. And also, for example, we can solve this new identity for sine theta. And we end up with sine theta equals 1 over cosecant theta. That's, of course, nothing new. Reciprocal relationships always work like that. And of course, all of these are only when well defined when the denominators are not 0. That goes without saying. Yeah, for the next one, we get cosine theta secant theta equals 1. And we can now solve that for cosine theta to get equals 1 over secant of theta. Next over, we can go ahead and cross multiply again. We can get tangent theta times cotangent theta equals 1. And we can also solve that for tangent of theta to get tangent of theta equals 1 over cotangent of theta. So extremely simple, but we'll be using them quite often. Closely related to these reciprocal identities are the quotient identities, which we have also seen before. And the first one has to do with tangent. We know that the tangent of theta equals sine theta over cosine theta. And we also know that the cotangent of theta equals cosine theta over sine theta. So if we go ahead and cross multiply again after imagining a 1 under both tangent and cotangent, we get cosine theta tangent theta equals sine theta, and we can also, for instance, solve this for cosine theta and get cosine theta equals sine theta over tangent theta. On this side, we can get sine theta cotangent theta equals cosine theta, and this time solve this for sine theta to get cosine theta over cotangent theta. And the main thing is not to worry about all the things you have to memorize, because you basically are going to know the key ones, and the others can quickly be derived from those. But just showing you the possibilities here from just one of these equations at a time, you get three different versions that can be useful to us, as you can see, in various instances. Make sure you understand these most basic identities before we proceed. Next, we're going to look at what are known as the even-odd trigonometric identities. And before we actually consider the trigonometric aspects of evenness and oddness, we want to do a general discussion of what those two words mean as far as functions are concerned. So a function f is said to be even if f of negative x equals f of x for all x. And right now we're dealing with real functions for all x belonging to the set of real numbers. So one of the most familiar even functions is, let us consider f of x equals x squared. Notice that if we look at f of negative x, that means wherever we see x in the definition of this function, we're going to replace it with negative x, and we end up with negative x quantity negative x squared. And as you know, when you square negative 1, you just get 1, so you end up with x squared, which, as you notice, is the same as the original f of x. So therefore we say f of x equals x squared is an even function. Now, if we consider the other variety of functions, they're known as odd functions. So we say a function f is said to be odd if f of negative x equals negative f of x for all x belonging to the set of real numbers. Notice this upside down A symbol in mathematics stands for all. Since we have to do a lot of writing of the same phrases over and over again, we usually come up with symbology to make it a little bit quicker for us. So here's an example of a very familiar odd function. Consider f of x equals x cubed this time. Notice that if we consider f of negative x, we replace x with negative x in the original function, we get quantity negative x cubed. This time negative 1 to the power of 3 is going to remain negative, so we get negative x cubed. And remember, the original function was x cubed, so negative x cubed is actually the opposite of the original function. So we say equals negative f of x. Therefore, f of x equals x cubed is an odd function. Okay, of course, some functions are neither even nor odd, but right now we want to focus on these two types of functions and see how they tie in with the trigonometric functions that we know. See how we can categorize the 6 different trigonometric functions that we are familiar with. So make sure you understand this before we go on. Now we'll look at some graphs that are going to help us understand the even and odd nature of sine and cosine, and using those we'll be able to determine the even and odd nature of the other trigonometric functions. Let's start with the cosine function. Recall that on the unit circle, which we have here, when you look at an angle in standard position, the initial side is always the positive x-axis, and the terminal side could be anywhere along the circle. So here we're looking at a what we call a first quadrant angle, theta, and we recall that the x-coordinate of the point of intersection of the terminal side of the angle with the unit circle is in fact the cosine of the angle, and the y value is the sine of the angle. So we also notice that for theta and negative theta here, which are first quadrant angles, the x value remains the same. And we also notice the exact same thing happens even if we look at a second quadrant angle here. The x values will both be negative x here, or a third quadrant angle here, again for both theta and negative theta. Of course, theta is a third quadrant angle, but its opposite will be a second quadrant angle, but nevertheless the x values are the same. And the same happens if we look at a fourth quadrant angle. And of course, these could be much larger angles with larger number of rotations, but that doesn't change our discussion here. So as it turns out, so whether we're looking at theta or negative theta, the cosine of both is the same. And as we just discussed in the previous screen, this makes the cosine function an even function, because cosine of negative theta is the same as the cosine of theta. Again, cosine of negative theta, negative x here, is the same as the cosine of theta. And for all of them, the same thing holds. Sine, however, does the exact opposite. Notice that, for example, for this angle in this first quadrant angle theta, when you look at the sine of negative theta, it's actually negative y, whereas the sine of theta is y. And the same goes for this second quadrant angle and its opposite, which is of course going to be a third quadrant angle. Notice the sine values are opposites, again here and finally here. So we can see that the sine of negative theta is always going to be the opposite of the sine of theta. So we conclude that the sine function is an odd function. Make sure you look at these pictures closely and understand them to fully grasp what we just discussed before you continue. So as we just observed, the sine function is an odd function, which means sine of negative theta equals negative sine of theta, and the cosine function, on the other hand, is an even function. So cosine of negative theta is actually going to be the same as the cosine of theta. So here we have an odd function, and here we have an even function. And of course, once we know this, we can determine the nature of all the other 4 trigonometric functions as well. For example, we know that the cosecant of negative theta is going to be 1 over the sine of negative theta, which is 1 over, as we see here, negative sine of theta. So but we know that 1 over sine theta is cosecant theta, so we get negative cosecant theta. So therefore, the cosecant function again turns out to be odd. And for secant of negative theta, we see that we get 1 over the cosine of negative theta. And as you know, cosine of negative theta is the same as cosine of theta, which is secant of theta. So we can see that the secant function, again, because f of negative theta equals f of theta, is going to be even. As for tangent and cotangent, we can see that the tangent of negative theta is the sine of negative theta over the cosine of negative theta. Now we know the sine of negative theta is negative sine theta, and that the cosine of negative theta is cosine theta. So we get negative sine theta over cosine theta, which is of course negative tangent of theta. So notice that the tangent of negative theta is the opposite of the tangent of theta. And of course, this makes the tangent function odd. And finally, for the cotangent of negative theta, we know that's the cosine of negative theta over the sine of negative theta, which is going to be the cosine of theta, because the cosine function is even, over negative sine theta, because again the sine function is odd. So we end up with negative cosine theta over sine theta, which is of course negative cotangent theta. So cotangent of negative theta ended up being negative cotangent theta, making it odd as well. So as you can see, the sine, cosecant, tangent, and cotangent are all odd. The cosine and the secant are the ones that turn out to be even. Next, we're going to look at what are known as Pythagorean trigonometric identities, and they all start with sine squared theta plus cosine squared theta equals 1, which we've seen previously. And of course, that's very easy to see once we're familiar with the unit circle, because if we take any angle theta, we can see that the point of intersection with the unit circle of the terminal side of theta, xy, is going to represent the cosine of the angle and the sine of the angle. And of course, just looking at this from a purely geometric point of view, we have a triangle, which is a right triangle here, and this side here will be x, this side will be y, and the hypotenuse, of course, is a radius of the unit circle, which, as we know, has length 1. So by the Pythagorean theorem, we have x squared plus y squared equals 1, replacing x with cosine of theta and squaring it, and y with sine of theta and squaring it, we get 1. And we normally write this with starting with the sine squared theta. Notice that when you take a quantity such as sine theta and square it, you want to make sure you put the square in this location when you want to remove the parentheses, not on top of the theta, because then it'll be misinterpreted as meaning that you're going to square the angle and then take the sine. So be very careful with that. And then plus cosine squared theta equals 1. So that's simple enough to understand, and that's where the Pythagorean identities begin. Now, obviously, doing some very simple algebra with this, such as, for example, we can take both sides of the Pythagorean identity and we can divide by cosine squared theta, and we end up with sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. So we know that sine squared theta over cosine squared theta over here is just going to be tangent squared theta plus 1, which will give us secant squared theta, because if you recall, 1 over cosine theta equals secant theta. So this would be our first Pythagorean identity. This is the second one, which we have derived from the first one. And if we start with the first one again, and this time divide both sides by sine squared theta, then let me skip that one step and just go ahead and throw a sine squared theta under each of these, because we know that splits up. And on the other side we have sine squared theta. So this time, if you notice, we end up with cosine squared over sine squared, which is cotangent squared. So if we write that first, we end up with cotangent squared theta plus this quantity, which is of course 1, equals cosecant squared theta. Again, just as in the case of the reciprocal identities, you need to recognize these in various forms. For example, the first one gives us two offshoots. We can solve it for sine squared theta, and we know that that becomes 1 minus cosine squared theta. Or we can solve it for cosine squared theta, which gives us 1 minus sine squared theta. So these are related Pythagorean identities, not the main ones. Now, this one we can do the same. We can see that if we solve it for tangent squared theta, we get 1 minus, secant squared theta minus 1. Or one thing we could do is we could go ahead and move this tangent squared to the other side, so we end up with secant squared minus tangent squared equals 1. So secant squared theta minus tangent squared theta equals 1. And we can do a similar thing here. So solving it for cotangent squared theta, we get cosecant squared theta minus 1. Or we can do the same trick we used here, go ahead and move the cotangent squared theta to the other side, so we end up with cosecant squared theta minus cotangent squared theta equals 1. I think you see what I meant in the previous lecture when I said we're going to get into trigonometric identities, and this is really going to recall much of your algebra abilities and skills. So that is basically what we mean by Pythagorean trigonometric identities. Make sure that you absorb these before we proceed. Okay, we're ready to go ahead and apply some of these fundamental properties that we learned today, fundamental trig identities. And here's an example that you may encounter. For example, here we're given that the tangent of a given angle is -4/3, and we're also told that this angle belongs to quadrant 2. Of course, we mean that's where the terminal side is, and we're asked to find the secant of the angle and the sine of the angle. So, of course, since we're given tangent, if we recall our the identities we just covered, the one of the ones that had tangent in it was tangent squared theta plus 1 equals secant squared theta. This will be a particularly good one to use because after all we're looking for secant of theta to begin with. So now we know what the tangent of theta is. It's -4/3. So here we're going to have to square that because we want tangent squared plus 1 equals secant squared theta. So now we get 16/9 plus 1 equals secant squared theta. And of course, if we go ahead and consider this 1 to be 1/1, then we can just multiply top and bottom by 9, and we end up with 25/9 equals secant squared theta. Now, this is the step where this restriction comes in very significantly, because we have to look at the unit circle and see the indications of that. So let me go ahead and bring in the unit circle. Normally, when we try to solve an equation like secant squared theta equals 25/9, we can get two solutions out of that. One is going to be the positive square root of 25/9, and the other one is going to be the negative square root of 25/9. But we notice that theta is an angle in quadrant 2, where we know the cosine values, which are the x values, are negative. And since secant is 1/cosine, we know that the the secant values are going to be negative as well. So we're only going to accept the negative square root of 25/9 as a solution. So secant of theta will be negative square root of 25/9, which gives us -5/3. So we have one of the values we were asked to find. Now we only need sine of theta. And there are different ways to get it, but one thing we notice is that if we know the secant, we also know the cosine, which is going to be the reciprocal of the secant. So it's going to be -3/5. And now that we have the cosine and the tangent, we can of course get the sine value. So if you remember, tangent of theta equals sine theta over cosine theta. So if we cross multiply, we get sine theta equals cosine theta times tangent theta. So now we substitute -3/5 for cosine theta, and we go ahead and substitute -4/3 for tangent of theta from what was given to us from the beginning, and we end up with positive. Actually, notice that the 3's cancel out, so we get +4/5. Of course, we'll just write that as 4/5, and that's going to be the sine of theta. So there we have both of the quantities that we were trying to find, and this first one was the secant of theta. So if we were to box our answers, it would look something like that. So this is how we can go about doing some of this. And of course, we have done problems like this previously where we utilized a graph and we drew the proper triangle to signify the situation, and we could do it that way as well. This is just an alternate way, and it's a more algebraic type of method. So make sure you can handle something like this before we proceed. Okay, so here's a really good problem that's going to prepare us for the more advanced identities we're going to encounter in our next session. So they want us to write sine of x in terms of cotangent of x alone, basically. So in other words, you want an expression describing sine which has nothing but cotangent in it. You may be thinking, well, cotangent is cosine over sine, can't we use that? Well, the problem is the cosine there. We want only to have sine and cotangent in relation to one another. So, but we did have an identity, if you recall, that didn't necessarily relate cotangent with sine, but it was a relationship between cotangent and cosecant, and that relationship was one of our Pythagorean identities, which was cotangent squared theta plus 1. Actually, we're using x here, let's be consistent. So cotangent squared x plus 1 equals cosecant squared x. So since I'm going to be deriving a formula for sine x, let me go ahead and write the cosecant squared x on the left side, which makes no difference. We could have worked with it on the other side, but this might be more visually pleasing. So since I'm trying to get an expression for sine, I know I can quickly turn cosecant squared x into 1 over sine squared x. So I get 1 over sine squared x equals cotangent squared x plus 1. So if we go ahead and invert both sides, we can, basically the rule says that if you have a over b equals c over d, then you should be able just to take 1 over both sides and end up with b over a equals d over c as well. So that's what we're going to do. We're going to take the reciprocal of both sides, basically. So we're going to get sine squared x equals 1 over cotangent squared x plus 1. Now if we just apply the square root property, we get sine x equals plus or minus square root of 1 over cotangent squared x plus 1. And the square root property, of course, says if x squared equals k, then x must be positive or negative square root of k. So we're almost could say we're done, because they wanted us to write sine and describe it in terms of nothing but cotangent. But as you know, this is going to involve a square root in the denominator, and we usually like to rationalize such denominators. So we're going to keep going. We're going to say that's equal to plus or minus square root of 1, which is just 1 over square root of cotangent squared x plus 1. And now we're just going to rationalize by multiplying the top and bottom of this fraction by this square root. So we're going to get square root of cotangent squared x plus 1 and square root of cotangent squared x plus 1, and we're almost finished. So we can now say sine x equals plus or minus square root of cotangent squared x plus 1 over, we know that the square root of anything times itself will just give the radicand, so over cotangent squared of x plus 1. And here we have expressed sine x in terms of cotangent alone. Okay, let's go ahead and look at one more problem before we call it the day. And here we're going to write this expression 1 plus tan squared alpha over 1 minus secant squared alpha in terms of cosecant of alpha. And we're providing a hint here that we should first write all trig terms using sines and cosines. And that is going to be one of the main strategies that we'll utilize as we encounter more complex trig identities in the next video. So we'll go ahead and start out by writing the expression that's given, 1 plus tan squared alpha over 1 minus secant squared alpha. And per the suggestion provided, we'll go ahead and rewrite both tan squared alpha and secant squared alpha in terms of sines and cosines. So instead of tan squared alpha, we can write sine squared alpha over cosine squared alpha over 1 minus, and we'll replace secant squared alpha with 1 over cosine squared alpha. Now we notice that we have a complex fraction, and the numerator of the complex fraction and the denominator both have a LCD of cosine squared alpha, so we'll go ahead and multiply both the numerator and denominator of the complex fraction by cosine squared alpha. So as we do that, we're going to distribute, so we're going to get that multiplied by each term because of the distribution. So we're going to get this kind of a situation. And now when we go through and simplify that, we'll end up with cosine squared alpha plus, here the cosine squares will cancel out in this term, so we just get sine squared alpha over cosine squared alpha minus, again these two cosine squares will cancel out and we get 1. So now we recall our trigonometric Pythagorean identities, which were, if you recall, sine squared alpha plus cosine squared alpha equals 1 was the very first one we looked at. And of course, cosine squared alpha plus sine squared alpha is the same as sine squared alpha plus cosine squared alpha. So we can replace that with a 1. Now we also notice there's cosine squared alpha minus 1. So if we just take this equation that we have here and move the 1 to the left side and the sine squared of alpha to the right side, we'll end up with cosine squared alpha minus 1 equals negative sine squared alpha. So we're going to go ahead and replace cosine squared alpha minus 1 with negative sine squared alpha. And of course we know that 1 over sine alpha is cosecant alpha, so this is just negative cosecant squared alpha. And we have completed the task that was required of us, which was to write this expression in terms of cosecant alone. So, and we've accomplished that. As a heads up, in the next section, these hints won't be provided, and we'll just be asked the same question, but it'll be asked in this way. You'll be asked to prove that 1 plus tan squared alpha over 1 minus secant squared alpha equals negative cosecant squared alpha. And of course, the way that we will do it is exactly what we just did here. So the difference is going to be that there won't be any hint provided. So here we're learning the techniques that we need so that we can handle a situation like this or an identity like this without needing any hints. And that should pretty much cover it for this section. So be safe until the next time we meet.